Let's now see how to perform automatic optimization in Turbo Design 1. And as we saw earlier, the runner component has the highest profile loss, and so it has the maximum impact on the stage efficiency as a whole. And so this is the component that we'll be optimizing. And apart from the profile loss, another issue we see here is the minimum pressure. And so if you have a look at the static pressure distribution on the runner in this plot here. Now, although this plot comes from the in-visit calculations, but we have seen quite a good correlation between this and actual CFD results. And so what we see here is that there is a significant negative pressure here at the shroud suction surface. And so what this means is that there is a strong possibility of cavitation in this area of the runner. And so in the optimization, what we are trying to do is we are not only going to minimize this profile loss, but at the same time we'll try to increase this minimum pressure in order to avoid the cavitation scenario as well. And in order to achieve that, we are going to try to vary the optimize the streamwise blade loading, and at the same time we are also going to try and optimize the wrap angle distribution or the stacking at the leading edge. For the baseline, the stacking was 0, so there was 0 wrap angle at the hub and the shroud. But now, since we have this problem at the shroud, we are going to try and modify the wrap angle at the shroud as well, along with the streamwise loading distribution. So in order to start the optimization, we can add an optimization like that. And we can see that the target case selected is the baseline runner, which we want to optimize. The workflow is rapid single point, which is basically direct optimization using MOVA approach. If we turn on all the plots, rearrange them a little bit, so let's start with the input parameters first. And we can see we already have the streamwise loading parameters selected as the input parameters for variation. But since we also need to modify the stacking, so we can add the wrap angle at the shroud, just like that. And now it's been added to the list of input parameters. And what we can see now is that by default, the range of variation or the lower and upper bound for each of these different parameters is minus 10% of the baseline value. But what we can also do here is we actually have an option, estimate input ranges. And what this does is it runs a machine learning based algorithm to calculate the optimum upper and lower bounds for each of these different parameters. And the reason we do this is we want to be able to explore a large design space, but at the same time we also try and avoid feasible solutions. And so we can select this, we can run the range optimizer by selecting this option, and then it will calculate the upper and lower bounds. And within 5 minutes or so, the range optimizer has estimated the optimal upper and lower bounds for each of these input parameters, as we can see here. And the next section is to specify our constraints for the optimization. So by default, the throat is already selected, and we have maintained this very tightly, plus minus 5% of the baseline value, because in case of Francis turbines, the throat determines the mass flow rate and thus the turbine power output, and so it has to be constrained very closely. And along with the throat, another constraint that we can specify, the secondary flow factor, which we can select like this. Now, although profile loss is more important in Francis turbines, but we still don't want to have very high secondary flows, very strong secondary flows, and so we constrain this to plus minus 10%. And then finally, we specify the optimization objectives, and we have profile loss selected as default. So, and we want to minimize this, of course, and we can remove secondary flow factor, and instead of this we can select the minimum pressure like this, and then we can choose to maximize it just like that. And as we saw earlier, we want to minimize the profile loss and increase the efficiency, and at the same time maximize the minimum pressure to remove cavitation scenarios. And once our optimization setup is complete, we can start the optimization run using this option here. So once the optimization run is complete, we can see all the designs on this scatter plot between the two objectives, the profile loss on the x-axis and the minimum pressure on the y-axis. And right now we can see all the solutions, and then we can choose to see only the convergent solutions, or else the feasible solutions, which basically respect the specified constraints, or we can also choose to see the Pareto front of the optimum solutions. And basically from this front we can choose any design of interest for further analysis. And so in this case we can choose this design here, and we pick this because it's somewhere in the middle of the front, and this should provide a good trade-off or a good compromise between the highest minimum pressure and the lowest profile loss, and so basically efficiency and cavitation aspects. And now to analyze this, we can simply choose analyze case here, and what this will do is it will run the optimum design, and then it will add it to our project manager window here. So very quickly it has run the optimum design, and which we can rename to the optimum runner, optimized runner. And we can now compare the performance parameters of this optimized runner to the baseline runner, and we can immediately see that the profile loss is much lower compared to the baseline runner, and also the optimizer has increased the minimum pressure significantly compared to the baseline. And at the same time, since we had constrained the secondary flow factor, it hasn't changed much from the baseline value. And also because of our throat constraints, the throat hasn't changed much, and it's within the specified bounds, and so our mass flow rate will not change from the baseline case. So let's now have a look at how the optimizer was able to achieve these results. So if we first look at the streamwise blade loading and compare it with the baseline runner, what we can see is, while the shroud loading is not very different from the baseline case, but for the shroud, actually it's the loading is much more aft loaded compared to the baseline runner. And we can also see how the design of the blade has changed because of this change in the loading. So in the 3D plot, we can actually compare the two designs, and if we select combine plots here and enable all the blades, then we can see that the optimized runner is quite different compared to the baseline runner. And what we can also see is that while the baseline runner had a radial leading edge, zero stacking, clearly the optimized runner has a forward stacking. So there's a forward lean at the leading edge of the optimized runner. And now let's have a look at how it changed the static pressure distribution. So because of the changes in stacking and the streamwise loading at the shroud, we can see that now the pressure is positive at the shroud suction surface throughout this region, where we were seeing this substantial negative pressure in the baseline. And now because of this raising of the static pressure in this region, we have positive pressure throughout, and this should actually help to avoid the cavitation scenario that we were seeing earlier. And so, since this design gives us promising results in case of in terms of profile loss as well as the minimum pressure, we can select this for CFD analysis and for comparison with the baseline design.